All right, let's go over the last little bit of notes and talk about circular orbits. So think back to the first lecture in this unit. We were talking about gravitation, right? And think back to when we talked about Newton's mountain, where Newton pictured himself to have a mountain, and on that mountain he placed a cannon that would launch a cannonball horizontally off the top of that mountain. And what he did is he imagined himself firing that cannonball with greater and greater and greater speeds. Well, eventually he surmised that at some initial velocity, the cannonball's drop in altitude would equal the curvature of the Earth, in which case the cannonball would never reach the ground. Right? It'd be in a perpetual state of free fall. Right? And so essentially, that cannonball would be in orbit. So anything that is orbiting, we consider to be in free fall. Right? Any orbiting projectile is by definition solely influenced by the force of gravity, and therefore by definition is in free fall, just as if you're dropping a tennis ball in the hallway. Right, so anything that orbits is in free fall. Now, one term you're going to pop up or see pop up quite a bit is this term satellite. A satellite doesn't necessarily mean something man-made. A satellite can refer to anything that is in a state of orbit. Um, so whether you're talking about the International Space Station or a moon, right? A moon is a satellite of the Earth, right? So just keep that in mind that if you do see the term satellite, it doesn't necessarily just mean something that's man-made. It can be a natural satellite. And those natural satellites are also in a state of free fall because, by definition, they are orbiting. The only force acting on them is the force of gravity. So take a look at example 6.4. We got a satellite in a low Earth orbit. Which of the following changes would increase the orbital period? So go ahead, pause the video, see if you can't figure that out. Well, first off, let's take a look at how we could discover mathematically the period of something in orbit. Well, we know that the speed of something traveling in a circle is equal to distance, right, the circumference of a circle, over time, in this case, the period. Well, if we rearrange that, we get that the period is equal to 2 pi r over the speed. So now we can go through our options here. So increasing the mass of the satellite. Well, notice mass isn't involved in here at all, so we don't have to worry about mass having a relationship on that period. So we can toss out option A. Let's jump down to option C, increasing the value of g. Well, if you increase the value of g, that gravitational acceleration, what you're going to be doing also is increasing the value of v, right? Since your centripetal acceleration is equal to v squared over r, and in this case, that centripetal acceleration would be that acceleration due to gravity, right? So if you increase g, you're also increasing v squared if that radial or the height of the orbit remains the same. So we can cross out C. Now if we look at B, increasing the height of the satellite above the surface, well, if we increase R, right, the height at which it orbits, we also increase T, the period of rotation. Right, so B is the only choice that makes mathematical sense. Now, we can also derive a formula for the speed required for a satellite to maintain a circular orbit. Now, anything in orbit, right, if we were to draw a free body diagram for it, so let's say this is the Earth right here at the center, and this is the moon. Well, the only force acting on that moon orbiting the Earth, or the Earth, is that force of gravity. Right? So if we look at Newton's second law, that net force equals mass times acceleration. Well, our net force in this case is the force of gravity. And so let's be a little more generic here and define what this mass is. This is the mass of the object in orbit. So let's call it m sub o, right, for a massive object. Now we can take this a step further. We know the law of universal gravitation tells us that force of gravity is equal to G times two masses, which in this case would be the well, let's redo that. G and two masses. And in this case, let's say that your big M is the mass at center of orbit, so the planet, and your little m is going to be mass of object. Right, just to make our lives easy. So big M is whatever is at the center of the orbit, and then little m is going to be whatever is orbiting that big M. And that is all over a distance squared. Well, we can set that equal to the mass of the object times its speed squared over its orbit. Right? Because again, all we're doing is plugging in the law of universal gravitation here for force of gravity. Now notice what happens. The mass of the object goes away. So the mass of the orbiting body has no effect on the orbital speed. Right? It doesn't matter if you have a International Space Station out in orbit, or if you have I don't know, a tennis ball. Right? The mass of the object itself plays no part in determining the speed of your orbit. Notice we can also cancel out an r. And so we're left with gm equals v squared, gm over r, sorry. Which, if we solve this out fully, gives us that our speed is equal to gm over r square root. Right, so the speed of anything in orbit depends entirely on that universal gravitation constant, the mass of whatever it's orbiting, so usually a planet in our case, and the height above the center of that planet itself. Right, so r is going to be distance from center of planet. Right, so not just distance from the surface, right? It's the distance from the actual center of whatever it's orbiting. And again, notice that your object's mass plays no part in this, right? All that matters is that constant, the mass of the planet, and the distance from the center of the planet itself. Right, that's going to determine the speed at which something maintains a circular orbit. But also keep in mind that this formula is for a circular orbit. Right, so if an object is orbiting at a speed that's greater than what this formula gives you, that means that's going to be in an elliptical orbit. Right, so any faster gives you an orbit that's not circular, rather it is elliptical. Now, we can also derive a formula for the period of anything in orbit. So we know that the speed of anything in orbit is related to 2 pi r, its orbital distance, and t, the period. So let's go ahead and plug in the equation we just derived for something that is in a circular orbit. So v we could replace with gm over r, and set that equal to 2 pi r over t. Alright, let's get rid of the square root. It's always nice not to have, any square roots laying around. So gm over r is equal to 4 pi squared r squared over t squared. Or gm is equal to 4 pi squared r cubed over period squared. Or if we go even further, we can say that period squared is equal to 4 pi squared over gm times r cubed. Right, so in this would allow us to calculate the period of anything that is in a circular orbit. And again, keep in mind, just like in the previous equation, the m here, try to make it capital again, the m here is the mass of whatever's at the center of the orbit, so the planetary mass. Right, again, r is the distance from the center of that planetary mass. So let's take a look at example 615. So we want to locate a geostationary satellite. So your communication satellites appear to hover over one point on the Earth's equator. These are your geosynchronous or geostationary satellites, right? They're used for communications a lot. And one of these satellites appear to be stationary as the Earth rotates. We want to know the radius of the orbit of such a satellite. All right, so with these communication satellites, you got to put them at a certain orbital distance so that they maintain a constant communication with the same portion of Earth at all times. Right, so things like GPS, those sort of satellites. Well, the first thing we're going to need to know is, well, it would be good to get the mass of the Earth. So let's look that up real quick. And we find through a quick Google search that the mass of the Earth is 5.972 times 10 to the 24th kilograms. Now we're looking for that orbital distance. Now, the one thing you got to keep in mind, we need to be able to identify the period of one of these satellites based solely off of what we know about geostationary satellites. So again, these satellites, they hover over the same section of Earth at all times. So they would have to have the same period of rotation as the Earth, right? So the period of rotation would be 24 hours, right? Or if we want to get that into seconds, 1 hour is 3,600 seconds. So the period would be 86,400 seconds. So we got mass, we got period. We know g is that constant, 6.673 times 10 to the negative 27. Or negative 11th, rather. Alright, my bad. So 6.67 Newton meters squared per kilogram squared. Alright, so we've got everything we need in order to find the period. Now, it might be helpful to rearrange this a little bit. So we could have t squared times gm over 4 pi squared equal to r cubed, right? Or r would be equal to t squared times gm over 4 times pi squared and cubed root. Now keep in mind here, pi is the only thing being squared already, right? That had already been squared earlier. Same thing up here, period is the only thing being squared. So go ahead, plug everything in, let's see what we get. And you should get 4.22 times 10 to the 7th meters. And again, that's the distance from the center of the Earth, not from the surface of the Earth. If you're not sure how to get the cubed root in your calculator, right, remember that you can always, rather than the cubed root, put whatever's inside here to the power of 1/3, right, and it'll do the same thing. Alright, so in Stop to Think 6.6, we're told that each year the moon gets a little bit further away from the Earth, increasing the radius of its orbit. How does this change affect the length of a month? Now, this question is kind of awkwardly worded because you would say, well, the month doesn't change, right? We've got a calendar. Well, this question is kind of assuming that we're running off of a lunar calendar rather than the Gregorian calendar, right? So a lunar calendar would be dependent on the phases of the moon, meaning where the moon is in its orbit. So if the moon is getting further and further away from the Earth, and we look at our equation here, if r goes up, actually let's look at this version of the equation, makes your life easier. If r goes up, what happens to the period of rotation? Well, the period of rotation is also going to go up. So if the period of rotation of the moon goes up, then if we were following a lunar calendar, our month would become longer and longer and longer over time. And so the last thing we want to look at is let's put everything together from stuff all over the year. So an integrated example 616. We've got ourselves a Stone Age hunter, and he's overlooking a flat plain. He places a 1 kilogram rock in a sling, ties the sling to a 1 meter long vine, then swings the rock in a horizontal circle around his head. The plane of the motion is 25 meters above the plane below. Tension in the vine increases as the rock goes faster and faster. Just as tension reaches 200 newtons, the vine snaps. If the rock is moving toward the plane at this instant, how far out on the plane from the base of the cliff will it land? Alright, so let's examine this in two different stages. Now we've got that circular motion here. Now this is going to be an overhead view of the hunter. Now, here's the rock. There's a force of tension here acting on the rock, and that's going to be the only horizontal force acting on it. Again, this is an overhead view of this scenario. And we know that that force of tension, when the vine snaps, is 200 newtons. We know the length of the vine is 1 meter, right? So that would be your radius. We know the mass of the rock is 1 kilogram. And then our second point of interest is this guy is on a cliff, right, hurling that rock around above his head, and it snaps. Now the key thing here to think about is when it snaps, right, that rock, due to its inertia, is going to fly off horizontally. So this rock becomes a horizontally launched projectile. And we want to know x, the range of that rock. How far away from the base of the cliff does it land? Now we also know that the vertical distance here is 25 meters. So these are all of our knowns and unknowns. And again, when you get a complex problem like this, draw it out thoroughly. Yeah, it takes a little extra time, but it's also good to make sure that you don't make any mistakes. Or at least reduce the chances of you making a mistake. Now, the first thing we're going to want to know, right, is we're going to want to know v naught x to eventually get x. Now, how can we find v naught x? Well, let's go back and examine how fast it's going when the tension reaches 200. So our net force is equal to mass times acceleration, and our net force in this case is just tension. Right, so 200 newtons is equal to 1 kilogram times unknown v over 1 meter. So solve out for v, and you get 14.14 meters per second. And so this speed that we just discovered, right, that represents your initial horizontal velocity. Now keep in mind, also, when we've got a horizontally launched projectile, your initial vertical velocity is 0. Now, in the horizontal, there's no acceleration. Right? The only acceleration with a projectile occurs in the vertical. So if we're looking for x, x is going to be equal to the initial velocity of that rock times the time. So we need to know the time that that rock is in the air, right? So between the vine snapping and it landing on the ground. Now, we don't have enough info in the horizontal to figure that out, but we can use the vertical dimension to figure that out. So we know initial vertical velocity, we know y, we know the acceleration in the vertical is g, 9.8 meters per second squared. So we just want to look through our kinematic equations to figure out which one would give us time. So we got y equals v naught yt plus 1 half acceleration times time squared. Well, v naught y is 0, right? So y is equal to 1 half gt squared, or 25 meters, is equal to 1 half of the acceleration due to gravity times our unknown time, and solve out for time. So 25 divided by 4.9, square root that, and we get a time of 2.26 seconds. So, if we want to know the distance, again, it's dependent on the initial launch speed in the horizontal and the time. So x is equal to 14.14 meters per second times 2.26 seconds. So x is equal to 31.9 meters away from the base of the cliff. And see what you'll find on a lot of the AP free response questions that deal with circular motion is that they tend to tie the circular motion in to horizontally launched projectiles. Right? They always start with a scenario where something's spinning in a circle, then it snaps, and then becomes a horizontally launched projectile, and you want to find usually the range of that projectile. So keep in mind that these two concepts are often tied together in AP exam free response questions. Now, other than that, plan on testing mid next week, tentatively for now. So make sure you're keeping that on the radar and keeping pace with stuff. I'm not going to go through Kepler's laws of planetary motion. Just read through them in the notes. They're pretty straightforward, and really that's all you need to know about them. If even that, I think I've seen Kepler's laws pop up maybe once in a decade. But yeah, if you've got any questions, you know where to find me, and I will see y'all soon.